Good morning, everyone. I am Mridul Devnath from the Department of Electrical and Electronic Engineering, American International University, Bangladesh. Today, I will present our work entitled Resilience Phase Analysis of Hierarchical IoT Networks using a quantum-inspired spectral entropy framework. This work was conducted in collaboration with researchers from Lamar University, USA, and AIB Bangladesh. Now comes why resilience matters. Hierarchical IoT communication networks are widely used in smart cities, industrial automation, environmental monitoring, and many other cyber-physical systems. These systems rely on continuous communication between sensor nodes, gateway nodes, and core infrastructure. However, when a critical gateway fails, a large number of dependent devices may become disconnected. Furthermore, failures do not always remain local. They can propagate through the network and trigger cascading disruptions. Therefore, a more comprehensive resilience assessment framework is needed. This motivates the central question of our work. How can resilience be evaluated beyond connectivity alone in hierarchical IoT communication networks? Here, we reviewed prior research on IoT resilience, spectral graph analysis, entropy-based robustness, cascading failures, and recovery mechanisms. However, these aspects are usually investigated independently. Most studies focuses on only one resilience dimension, and spectral connectivity and entropy metrics are rarely combined, and cascading failures and recovery are one analyzed separately. And in addition, hierarchical IoT architectures remain relatively underexplored. To address this gap, we propose a unified quantum-inspired spectral entropy framework that jointly captures connectivity, structural uncertainty, cascading failures, and recovery dynamics. Here, the main contribution of this work is a unified spectral entropy framework for hierarchical IoT resilience analysis. Specifically, first, we introduce a composite resilience metric combining connectivity robustness, algebraic connectivity, entropy, and service availability. Second, we perform cascade aware phase analysis to identify resilience regimes under varying disruption conditions. And thirdly, we incorporate progressive recovery mechanisms to evaluate post-disruption restoration behavior. And finally, the framework is developed specifically for hierarchical IoT communication architectures and support random failures, targeted attacks, and recovery. The proposed system follows a three-layer hierarchical IoT architecture. At the bottom, sensor nodes collect environmental or operational data. The gateway layer performs aggregation, protocol conversion, local processing, and routing functions. And above that, the core communication layer provides a large-scale transport and connectivity to cloud services. Although this hierarchical structure improves scalability, it introduces concentrated vulnerability at gateway nodes. Since many sensors depend on a limited number of gateways, failures at these nodes can significantly affect connectivity and service continuity. To evaluate resilience comprehensively, we combine four complementary matrices. First is connectivity robustness, represented by the normalized giant connected component. Second is algebraic connectivity, denoted by lambda 2, which measures structural cohesion and resistance to fragmentation. Third is von Neumann graph entropy, which quantifies structural uncertainty and network organization using a quantum-inspired density matrix representation. Fourth is service availability, representing the fraction of sensors that remain connected to the core layer. These four indicators are integrated into a composite resilience score. The key idea is that resilience should reflect not only connectivity but also structural integrity, uncertainty, and operational functionality. To simulate realistic network behavior, we consider multiple attack scenarios. These include random node failures, degree-based attacks, betweenness-based attacks, and tire-aware attacks targeting gateway and core nodes. After an attack occurs, load distribution may trigger cascading failures. A node fails when its redistributed load exceeds its capacity, which is controlled by the cascade tolerance parameter alpha. The cascade process continues until no additional overload induced failures occur. After stabilization, recovery begins through progressive restoration of failed nodes. Here, our framework captures the entire resilience lifecycle as attack to cascade, then recovery, and after that, resilience evaluation. Now comes the experimental setup. Here we generated networks containing 200 nodes. The hierarchical IoT architecture consisted of 70% sensor nodes, 20% gateway nodes, and 10% core nodes. Here, initial failure fractions ranged from 0 to 0.4, while cascade tolerance varied from 0.05 to 0.5. We performed 100 realizations for each scenario. Performance was evaluated using GCC ratio, algebraic connectivity, entropy, service availability, and the composite resilience score. This figure compares resilience under different attack strategies. The blue curve shows random failures. Resilience decreases gradually because failures are distributed randomly across the network. However, targeted attacks produce substantially greater damage, and degree-based attacks remove highly connected nodes and rapidly reduce resilience. And betweenness-based attacks disrupt critical communication paths. The most severe degradation occurs under tier-aware attacks targeting gateway and core nodes. And this result confirms that gateway infrastructure represents a major resilience bottleneck in hierarchical IoT networks. This slide represents the resilience phase diagram. The horizontal axis represents the initial failure fraction, while the vertical axis represents cascading tolerance. We observe three operational regimes. In the high tolerance region, networks remain resilient and cascades are effectively contained. In the transition regime, small parameter changes led to significant resilience losses, and in the low tolerance region, cascading failures dominate network behavior, and resilience collapses rapidly. Therefore, resilience depends jointly on disturbance magnitude and overload tolerance. This slide illustrates network behavior during cascade propagation and recovery. On the left, node failures trigger load redistribution. The redistribution load creates overload stress, which can produce additional failures and prolong the cascade process. On the right, progressive restoration gradually reconnects nodes and communication paths. As connectivity improves, service availability increases and resilience recovers. An important observation is that even moderate recovery resources can significantly improve network survivability after large disruptions. Here we examine the behavior of von Neumann graph entropy. Entropy provides information about structural organization and uncertainty within the network. Higher cascade tolerance generally preserves entropy and maintains network structure. As disruption intensity increases, entropy decreases, indicating structural degradation and loss of organization. And small fluctuations reflect topology reorganization during cascading failures and subsequent recovery. And overall, these results demonstrate that entropy complements conventional connectivity metrics and provides additional insights into resilience behavior. Several practical insights emerge from the study. First, gateway nodes should be prioritized for protection because they represent critical resilience bottlenecks. And secondly, increasing overload tolerance through capacity aware routing and adaptive load management can significantly reduce cascade propagation. And thirdly, recovery mechanisms are just as important as preventive protection. Finally, comprehensive resilience assessment require connectivity, spectral cohesion, entropy, and service availability to be considered together. In conclusion, we presented a quantum-inspired spectral entropy framework for resilience analysis of hierarchical IoT communication networks. The framework integrates connectivity robustness, algebraic connectivity, von Neumann entropy, and service availability into an unified resilience metric. Results show that targeted attacks on structurally critical nodes produce significantly greater damage than random failures. We also demonstrated that resilience depends strongly on the interaction between disruption, magnitude, and cascade tolerance, and the progressive recovery can substantially restore network performance. Future work will incorporate real-world IoT datasets, dynamic traffic models, and adaptive defense mechanisms. Thank you very much for your attention. I would be happy to answer any questions.